Back in the day, we learned about proper integrals. These were integrals that went from like a to b, and they were of some function f of x dx, and then we used the fundamental theorem to say that this was really capital F of b minus capital F of a, and then this is where f is an antiderivative of little f, or rather that f, capital F prime of x, is little f prime of x. Okay, the important things to note: we can only use this theorem or this idea if the function f is continuous on the closed interval from a to b. So on a to b, f must be continuous. Alright, otherwise we cannot use the fundamental theorem. Well, today we're going to break all the rules and learn about improper integrals. Bum bum bum! There are mainly two kinds of improper integrals that we're going to look at. The first one is what happens when instead of from a to b, you have infinity as one of your two limits. We're going to see how to deal with that. And the second thing is, let's say that we do have an integral from two real numbers a to b, but f of x is not continuous on this interval. So an example of that, f not being continuous, would mainly be integrating across a vertical asymptote, and so we'll see how to deal with that as well. Cool. Here's the first improper integral we'll look at. It's the integral from 1 to, infinity of 1 over x squared dx. Now, the graphical representation of this is we have 1 over x squared, which looks something like that, and we're trying to find the area between 1 and then just, off to infinity and beyond. You can't really go beyond infinity, but whatever. Alright, so the way that we're going to do this, there's the official way, so this is the quote-unquote official way of doing it, and this basically relies on the fact that you cannot plug in infinity as a number. So what we do is we say, well, we can't do this integral unless this is a number. So what we say is we invent this limit, and we say b is going to approach infinity, and we rewrite the integral to have 1 and b in it, rather than 1 and infinity. So b is a number, and then we're going to take that number to infinity. Kind of a weird way, but this is the official mathematical way of doing it. Alright, so we have limit b, I'll keep the infinity in blue because it's easier. Alright, and then the antiderivative of 1 over x squared, this is x to the negative 2, so we add 1 and divide. So we're going to get negative x to the negative 1, and we're evaluating this from 1 to b. Great. Plug in the limits, so we'll have the limit, the limits of integration, not the limit infinity yet. And so we'll get negative 1 over b minus a negative, so plus 1 over 1, like this. And now we can take the limit as b goes to infinity. As b goes to infinity, we get 1 over infinity. This piece goes to 0. And then our answer, ooh, look at that. Our answer is simply 1. So that means that the area under the curve of y equals 1 over x squared from 1 to infinity, this blue area here has an area equal to exactly 1. So it's kind of weird that you can have like an infinitely long area, but it does converge to a number, and that number here is 1. Alright, the official way is kind of tedious because you have to remember to introduce the limit and then say, oh, b is approaching infinity, and then plug the limit back in. It seems kind of weird. Here's the unofficial way, and it basically, you're plugging in infinity as a number. Now, you can't technically do this, and some mathematicians might get angry at you for doing this, but hey, I'll give you permission for this class to do this. So let's say we have the integral from 1 to infinity of 1 over x dx. I would make a note of saying, oh, it's infinity, therefore it's an improper integral, but you can basically treat it the same as a regular integral. What's the antiderivative of 1 over x? If you said natural log of the absolute value of x, you are correct. And we're evaluating this from 1 to infinity. Great, now we just plug in the limits, just like normal. So it's the natural log of the absolute value of infinity minus the natural log of 1. Now, you got to do a little thinking here. The natural log of infinity, well, that's like what power of e gets you infinity. Well, this is going to go to infinity. So you get infinity minus the natural log of 1, don't think too hard, the natural log of 1 is 0. So you get infinity minus 0, which is infinity. And so therefore this integral diverges. We say that the integral diverges because it does not go to a number. Okay, graphically speaking, here's the function y equals 1 over x, and we're integrating from 1 to infinity, so we have this blue area again. And this blue area goes to infinity, which is weird because this blue area, which looked almost the exact same as this blue area, was 1, and 1 and infinity are very different numbers. But the key here is looking at what you are integrating. Okay? Notice that here we were integrating 1 over x to the first, and here we were integrating 1 over x squared. Ooh, tricky. Okay, and if you do a little bit of thinking, you can come up with the idea, or the property, rather, that if you have 1 to infinity of 1 over x to the p, where p is any number, really any positive number, let's say that p is greater than 0. If p is negative, then that would be silly, because then it would just pop up to the top. But anyway, so if you have an integral of this form, this integral will converge, as in it will go to a number. This integral will converge if p greater than 1. P has to be greater than 1. We saw that if p equals 1, then you get the integral of 1 over x to the first dx from 1 to infinity, and we saw that this diverged to infinity. But if you do like the integral of 1 to the infinity of 1 over x to the 1.1 dx, when you integrate this, remember that, so let's think about this. This is x to the negative 1.1. Oops, too many ones. So you add 1 to the power, so you get x to the negative 0.1, divide by the new exponent, which is like divided by 0.1. But now when you plug in infinity into this, because that's 1 infinity, because this is a 1 over x, then that term will go to 0, and you'll end up plugging in 1 and getting an answer. So the idea here is that this integral will converge basically if the power on the bottom is bigger than 1. And this is something that will come up later when we do sequences in series. The other type of improper integral is what happens when you integrate across a vertical asymptote, or rather if one of your limits happens at a vertical asymptote. Notice here that 0 really doesn't make this integral very happy, because then we get like we're integrating 1 over 0, and that's kind of weird. Okay, now first thing, do not just automatically say that this goes to infinity because, oh, we have 1 over x to the first. And the reason you cannot automatically say that is because this top limit is not infinity, it's 1. So you can't just jump to conclusions right there. So let's think about what's happening here. We have the function 1 over x, and it looks like this, just like last time. Haha. And now we're going from 0 to 1, and so really we're starting our integral here and we're ending here. And notice that 0 here is a vertical asymptote, so we're trying to find this possibly infinite area, but it extends infinitely upwards to infinity along the y-axis this time. Alright, let's go ahead and integrate this. So we can use the unofficial way. I'll just plug in 1 and 0. The antiderivative of 1 over x is ln of the absolute value of x, and we're evaluating this from 0 to 1. And so we don't think too hard. We plug in 1 minus natural log of 0. Okay, very nice. The natural log of 1 is 0. Great. And the natural log of 0, think about the graph of natural log. There's y equals ln x. And as I approach 0, okay, 0 is over here, and as I approach 0, notice that the y values go all the way down to negative infinity. So really, the natural log of 0 is negative infinity. Kind of weird, but this ends up being positive infinity, like that. And so, in fact, this blue area does diverge to diverges to positive infinity because the integral diverges. So when you're doing an improper integral, the first thing you want to look for is one of the limits of integration infinity or negative infinity? Limits of integration plus or minus infinity, or are we integrating across, or does the integral, does one of the limits of the integral, is that a vertical asymptote, or integral includes a vertical asymptote? Those are the things that will indicate that we have an improper integral, and then you can basically use the official or unofficial method to evaluate them. Hooray!